Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Good day, everyone. Today, we will explore the fascinating world of blockchain technologies. We'll dive into key concepts like distributed consensus in open environments, consensus in a Bitcoin network, proof of work. Let's get started. Slide 1. Distributed consensus in open environments. Introduction. To start, let's talk about what distributed consensus means and why it's so important in blockchain systems like Bitcoin. At its core, distributed consensus is about reaching agreement among independent participants in a decentralized system. The key challenge is that these participants may not trust each other. 1. In a decentralized network, no single authority controls the system, making it essential to have a robust mechanism to ensure everyone agrees on the same state of data. 2. This is particularly crucial in open environments where anyone can join the network, and there's no prior trust between participants. Key aspects. No central authority, unlike traditional systems controlled by a single entity, e.g., banks. Decentralized networks distribute control, reducing dependency on a central point. Trustless system. Since participants don't need to trust each other, the system uses algorithms and cryptography to ensure security. Transparency. Every participant can verify transactions, promoting fairness and accountability. Significance. This setup is the foundation of blockchain's security and reliability. It enables participants to work together securely, even when they don't trust each other. Example. Bitcoin's consensus mechanism ensures all participants agree on valid transactions and maintain consistent copies of the blockchain. New term explanation. Decentralized network. Think of it as a peer-to-peer system where no single party has overarching control. For instance, file-sharing networks like BitTorrent work on similar principles. Slide 2. Challenges in distributed consensus. Part 1. Distributed consensus is critical but challenging to achieve. Let's examine the major hurdles that blockchain networks face in open environments. Byzantine generals problem. This problem highlights the difficulty of reaching agreement when some participants may act maliciously or fail to communicate reliably. In blockchain terms, it means some nodes might validate false transactions, but the system must ensure they don't disrupt the network. Example. Imagine a group of generals trying to coordinate an attack. Some may be traitors, but the honest ones still need a way to ensure consistent decisions. Lack of trust. In open environments, participants don't know or trust each other. This makes it hard to establish a reliable system. Without mechanisms like proof of work (PoW), attackers could easily undermine the network. Slide 3. Challenges in distributed consensus. Part 2. Malicious actors. These are participants who deliberately try to disrupt the network. They might validate invalid transactions, launch attacks like the 51% attack, where they gain control of over half the network's computational power, flood the network with false data to slow it down. Synchronization delays. Nodes are spread across the globe, leading to latency issues. For example, when one node updates, it takes time for others to receive the information. Temporary inconsistencies, like forked blockchains, may arise until consensus is restored. Scalability constraints. As the network grows, reaching consensus becomes slower and more resource-intensive. Bitcoin's current limit of 7 transactions per second is a clear example. Solutions. To tackle these challenges, blockchain systems use 1. Consensus algorithms, mechanisms like PoW and proof-of-stake (PoWs). 2. Network optimization, techniques like sharding or sidechains. 3. Cryptography. Strong encryption ensures data integrity and prevents tampering. Slide 4. Consensus in a Bitcoin network. Definition. Bitcoin's consensus mechanism ensures agreement on the blockchain state. This prevents double spending, where the same Bitcoin is spent more than once. How it works. 1. Transactions are broadcast to the network and validated by nodes. 2. Miners group these transactions into blocks and compete to solve a cryptographic puzzle using PoW. 3. The miner who solves the puzzle first adds the block to the blockchain. 4. All nodes update their copies of the blockchain to reflect the new state. Significance: this process ensures security, transparency, and consistency, making Bitcoin a reliable and decentralized currency system. New term: double spending. This occurs when someone tries to spend the same digital currency more than once. Bitcoin's consensus mechanism prevents this by verifying every transaction. Slide 5. Proof of Work PoW. Definition: proof of work is a consensus mechanism where miners solve complex mathematical puzzles to validate transactions and create new blocks. It ensures only participants who expend computational effort can influence the blockchain. Process overview. 1. Miners adjust a variable called the nonce to generate a hash. Point 2. The hash must meet a specific difficulty level, e.g., starting with a certain number of zeros. 3. The first miner to solve the puzzle broadcasts their block to the network. Point 4. The network verifies the solution, and the block is added to the blockchain. Significance: PoW adds security by making tampering computationally infeasible. Without it, attackers could alter past blocks and disrupt the blockchain's integrity. Examples of terms: nonce. Think of it as a trial and error variable miners tweak to find the correct hash. Hash. A digital fingerprint of data, ensuring its integrity. Slide 6. Key features of proof of work. 1. Energy intensive. Mining requires substantial computational power, which enhances security but raises energy concerns. Point 2. Difficulty adjustment. The network recalibrates the puzzle's difficulty every 2016 blocks to maintain a consistent block time, approximately 10 minutes for Bitcoin. 3. Cryptographic hash function. Functions like SHA-256 generate secure, tamper-proof hashes. Point 4. Decentralization. Anyone with resources can participate in mining. 5. Immutability. Changing a block requires remining all subsequent blocks, making it virtually impossible. Example: Bitcoin's use of SHA-256 ensures high levels of data security and integrity. Slide 7. Advantages of proof of work. 1. Robust security. Tampering requires massive computational effort, deterring attacks. 2. Decentralization. Promotes a trustless environment where no single entity controls the network. Point 3. Prevents double spending, ensures every Bitcoin is spent only once. 4. Transparency. All transactions are verifiable by participants. Point 5. Proven model. PoW has successfully secured Bitcoin for over a decade. Slide 8. Disadvantages of proof of work. 1. Energy consumption. Mining uses immense amounts of electricity, impacting the environment. 2. 51% attack risk. A majority of the network's computational power can manipulate the blockchain. Point 3. Expensive mining. Specialized hardware and infrastructure are required. 4. Centralization risk. Mining pools dominate the system, reducing decentralization. Point 5. Scalability issues. Low transaction throughput limits its use for large-scale systems. Example: Bitcoin's scalability challenges led to solutions like the Lightning Network for faster transactions. Slide 9. Real-world applications and alternatives to PoW. Applications. 1. Bitcoin, the first and most prominent cryptocurrency using PoW. 2. Ethereum, pre-2022, transitioned from PoW to proof-of-stake (PoS). Point 3. Blockchain security. Other cryptocurrencies rely on PoW for data integrity. Alternatives to PoW. 1. Proof-of-stake (PoS), energy-efficient and users-locked cryptocurrency is collateral. Point 2. Delegated PoS, consensus delegated to elected representatives for efficiency. 3. Proof of authority (PoW), trusted validators replace computational effort. New term: Lightning Network, a scaling solution enabling faster Bitcoin transactions by processing them off-chain.